Remember, we were looking at proportions. If we got one proportion, we could do a confidence interval with it. We could do a hypothesis test. We could even compare two different proportions against each other and do a hypothesis test and a confidence interval. All right, this chapter, we can take a look at multiple proportions at the same time. We're doing hypothesis tests for them. All right, on Friday, we did this thing called a goodness of fit. This is the key thing about a goodness of fit. There's only one population parameter. We looked at Skittles. Right? We got a whole bunch of Skittles. And that was our population parameter. And then we broke those Skittles up into different categories. So one population of interest, breaking them up into different categories, which was colors. All right, the problem that you worked on today in your warm-up, and this is true. Basketball coach has this problem all the time. At the end of the game, we're losing. You've got to pick somebody to foul. All right, so these are the shooting percentages or the shooting numbers of each one of the players. Let's go ahead and write these down. What was this guy? 72.2%. Okay, next one. 60. Okay, next one. 58.3. Okay. We might say, well, we'll just foul this person because they're the worst this year. And then that's probably what you're going to end up doing. But I'm wondering if this, based on this sample, is there any real difference in all these shooters? In other words, all the shots they're going to shoot for their lifetime. Is there really any difference? Can we conclude that with some degree of certainty just based on this sample? Now, what's the key difference between this problem and the goodness of fit that you did last time? Now there's 5 different populations. These are different people. Each one has their own shooting percentage for their career. So there's 5 different populations of interest. It isn't just Skittles broken up into colors. It's 5 totally different people. And each one has their own population percentage of their percentage of free throws for their lifetime. So really what we're going to try to figure out here is, based on this sample, is there really a difference here between these shooters? Now, one thing I could do it like I did in the last chapter. I could compare 2 proportions at a time. But how many hypothesis tests am I going to do to be able to compare all these against each other? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have to do 10 separate hypothesis tests to compare each person against the other person. That's what's cool about a chi-squared. I can do them all at one time and see if any of them are different than the others. Okay? And that's what a chi-squared test is going to do for us. So hopefully y'all drew a graph on this. I do see some differences. These 2 people look very different from each other. But is that significant enough based on those sample sizes for us to know that at least one of these is different than the others? And that's our goal in this particular problem. All right, let's go through all the steps. There's some subtle changes here. It's still going to be chi-squared. We're going to still use those tables. We're still going to find a chi-squared value using the same formulas. But things change here a little bit. All right, population parameter. Now, there are technically 5 different populations of interest, but I'll let you guys be lazy again, I guess. I actually gave those people numbers. So do a nice job of telling me what you've got here. It's the true free throw percentage of these 5 players. Lifetime. That's what we're looking for. If I don't find there's any difference between these 5 players for what they're going to shoot in a lifetime, I can foul any one of them. Doesn't matter. Okay, so a good write-up here, the true free throw percentage of the 5 players on the court at the end of the game. Population value. All right, we got a subtle change here now. Okay, what are we going to assume going into this problem? That there's no difference. They're all the same. Okay, so here's how I'm going to write this. See what you guys think. P1 is equal to P2 is equal to P3 is equal to P4 is equal to P5 is equal to 20%. Give me a look, James. What's up?
Why did you use 20%?
Why did I use 20%? Isn't that what we had to do here with goodness of fit? Right? Because there was only one population of interest, so didn't all of those percentages have to add up to 100%? But do we have that situation here? I mean, there's no way. These guys are shooting in the 60s and 70s. We're not going to assume they're all supposed to shoot 20%. So one difference when you have more population, they don't have to equal 100%. They can have their own percentages. They're probably all around 60 or 70%, right? So we're going to assume that all of their free throw percentages are the same. We don't know what it is. We don't have goodness of fit percentages this time. But we're going to assume that all the players for their lifetime are going to have the same shooting percentage until we can prove that different. Okay? Now, here's a couple of things just to keep in the back of your head. We can, you know the two proportion test that we did last time? Wasn't that our null hypothesis? You can do this chi-squared doing that. It works for two or more proportions. The only thing you got to be careful about is if you're doing a chi-squared test, the alternate is always not equal to. Right? So if I'm trying to prove one person's got a higher percentage than the other, I got to do it like I did last chapter. The alternate is always not equal to if you're doing a chi-squared test. All right, back to what we're doing. Hey, these guys are all the same. Girls are all the same. The percentages are exactly what they are. All right, slight change in our alternate. At least one shooting percentage is different. Not incorrect, right? We said incorrect before. Well, your shooting percentage is not incorrect or correct, right? We're just going to prove at least one of them is different. And there's your not equal to thing. Okay? If we come up with evidence, we'll have proven that one of those persons is different. At that point, then we can maybe go do individual hypothesis tests comparing two of them that are one-sided. Okay, but this is just kind of a, let's throw all these people in a bucket. Is there any difference between these people, really? Yeah.
Okay, so first in the nulls, so they all equal 20%, you still...
No! They don't equal 20%.
I know.
Okay.
You had that at first, that was also...
I guess I was trying to confuse you, right? No, that's why the different multiple population parameters is different than goodness of fit. If we were doing a problem like we did last night, where there's only one population of interest, they have to add up to 100%. Those percentages add up to 100%, right? When we're doing multiple population parameters, 5 different players, okay, we're just going to say that all the percentages are equal to each other. They don't have to be add up to 100%. Okay. Level of significance, this isn't life or death, right? I mean, I might make this 10%. I mean, I'm trying to sniff out if there's any difference in these shooters are all, so I can pick the right shooter to shoot this. So, if I pick the wrong person, I lose the game. Actually, that is life or death, isn't it? I'm thinking. All right, now we've got to do our assumptions. Now we have to do our box. Okay, we have to do our box before we do the assumptions because we've got to find out all of our expected values. All right, here's the second different thing. Okay. When we did that Skittles problem, we had like 600 Skittles, right? Every one of those 600 Skittles was in a box. Okay, each person is in a box. We need to create a table where each free throw is in a box. What we're going to create is those two-way tables. We did them many chapters ago. Okay? So we are going to create this time a box that is 2 by 5. You've done this before. We're going to put those free throw percentages into this box. We'll call this the makes. So this would have been 72, 62, 50, 121, and 42. Now the question is, where does the 104 go? We've done this before. Does the 104 go in a box anywhere, or is it a total? It's a total, right? So this could be like makes, and this could be misses. The 104 goes down here. I want every free throw in a box. So how many misses must there have been? Remember you did a trick question like this on a homework a long time ago when we were creating these two-way tables? So you got some work to do just to create the table. So if 72 is here, 104 is here, what's this, 32? Okay. All right, let's finish it off. This is the 89. So there must be 27 misses. No?
Oh.
90. So this must be 40. 172. So this must be 51. And 72. So this must be 30. This is the key thing. Every experiment that was done, in this case a free throw, every free throw, whether it was a make or a miss, is inside of a box. Just like with all the Skittles, we had 600 Skittles, but we were able to get them in a 1-by table. But in this case, each experimental thing that was done, in this case a free throw, it finds itself in a box. Now what was the next thing we always did when we created boxes like this, 2A tables?
Expected value.
Not yet. That's what we're going to have to do here is expected values. But back in chapter whatever, we did this.
Add up the total.
Remember the row and column totals? That was always the first thing I wanted you to do. It's critical here. Okay, so let's go ahead and figure out. You add those up for me, and let's get the row and column totals. We already got the column totals, which is good. What do you got on top? 347 made free throws. Okay, how many misses do we got? 180. And then how many total? I guess I should be able to figure that out. 7 to 527. So these add up to 527, and these add up to 527. All right, Annika's right. We have to find the expected values for each one of these 10 categories. Because that's what we're going to check on our assumptions. We have to have the expected values. We have the expected values to figure out our chi-squared. Okay, I need you to go back to last chapter. What did we have to do in our assumptions when we did a hypothesis test and we set the population proportions equal to each other? What did we have to go find? Say it out.
P-weighted.
P-weighted. P-hat weighted, remember? Because we had to use it throughout the entire problem. All right, I need you to remember that because we're going to do the same thing here. Okay, so you're not going to have to do this in the problem because I got a shortcut for you, but I just want to show you how this works. So what would be P-hat weighted for this problem? Actually, the numbers are right here in front of you, right? Was it all the successes over the total possibles? So what would it be here in this problem? 347 over the 527, which is point, let me throw that in there, 0.8, 68.5? So remember what this is. We have to assume they're all going to shoot the same percentage for their lifetime. What we're going to use is our sample for an estimate as to what that might be. So we're basically going to assume for this problem they're all going to be 65% free throw shooters for their lifetime. Okay, so we should be able to do this now. So then, if that's the case, if every shooter is 65.8%, how many do we expect this person to make? How'd you get this? How many do you expect them to make? What are you doing?
72 over 347.
He happened to make 72. That has nothing to do with how many we expect him to make. What'd you do? N times P weighted. So what would be the N? No. We're asking ourselves, okay, how many free throws are we expecting this person to make? We now know he's a 65.8% free throw shooter. At least that's what we're going to assume. So what'd you do mathematically? You took the 104 times the 347 over 527. Isn't that N P-hat weighted? Okay, now here's the shortcut I have for you. The actual formula I'm going to let you use for the expected value is the row total times the column total over the grand total. Take a look at this. Isn't this spot just going to be 104 times 347 divided by 527. Everybody see that? So this spot is just 104 times 347 over 527. Row total, column total, grand total. So, what's that guy? Give me the, how do I find the expected value there? It would be 172 times, whoa! Row total, column total, grand total. So this spot is 180 times, I heard some people saying that one, right? I'm right down here. So it's 180 times 172 over 527. It's just n times p outweighted, but that's just how it works. All right, somebody give me this number. What'd you guys get here? 68. Let's go to one decimal. 68.4. Okay. All right, so actually I've got two ways for you to figure this guy out. One way would be 180 times 104 divided by 527. Is there another kind of quicker way that we can figure out how many we expect the person to miss?
104 minus...
What's that?
104 minus...
104 minus this, and that's a lot quicker than throwing those three things into your calculator. Maybe. What is this going to be? 35.6. So really we just need to figure out these four and then do the subtraction. Go to work. Go complete your tape. So right, this guy would be 347 times 89 divided by 527. Take that value, subtract it from the 89. Let's complete our table. Remember, we show our work for one of these. Okay, so. Doing right here. So this would be 347 times 89 over grand total, 527. N times P outweighted, that's all we're doing. Just giving it a little simpler look. You can find that spot by multiplying the row and column total and dividing by the grand total. What do you got here? Say again. 58.562. Okay, 58.6. This guy would then be 30.4.
Yeah.
Okay, up here.
59.3.
59.3. 30.7 up here.
113.3.
113.3 down here.
58.7.
You up here.
47.4.
Okay, down here.
24.6.
Now, for the chi-squared calculation we're going to do later, should have all the numbers. You should have 10 of them in L1, all of your expected values in L2. All right, we're going to do a chi-squared calculation in a bit, but let's go back to finishing our problem here. Okay, now we can do our assumptions because we have all of our expected values. What about simple random sample? What do you think? Getting a lot of this. I don't think so. Is this are these a good simple random sample of all the free throws that person's going to shoot in a lifetime? No, it's pretty much a convenient sample, right? I'm just looking at this year. Okay, so there's an issue there. Could there be a bias? Yeah, maybe the person went to a free throw shooting camp over the summer, and so this is very different than what they were going to shoot their whole life. I don't know. I'm not sure. But there are some issues here, okay, with the simple random sample. I don't think it's a good simple random sample of all the free throws they're going to shoot in their life. So just keep that in mind. How about all the expected values? Yeah.
I'm just a little confused as to why we're looking at their free throw proportions for their whole lives when, like, the past year would be more relevant.
Well, you know, you're right. I mean, I'm going to pick this person. You know what I'm saying? I'm going to pick this person just based on what they're doing. But this is considered in the short run, right, for their whole life of shooting free throws. So in the short run, am I going to trust the short run? I mean, if there's 5 reds come up on a roulette wheel in a roll, am I going to put all my money on the other one? So, I mean, I'm just trying to look big picture here to see if there's really any difference in these free throw shooters or not.
So does it ever? Are we ever going to have to change our methods based on, like, what the problem is practically looking for?
Yeah, I mean, I'll be honest, I made this one up myself. So I just came up with these numbers and I thought it was a cool application. You'll see better applications that make more sense. Okay. But I mean, I think this is, I just made this up, but I think it's kind of legit, right? I mean, is there really any, I mean, this person only shot 90 free throws out of the thousands he's going to shoot in his career. I mean, is this really, you know, for sure? Or if it's a situation, because in a basketball game, okay, we'll get deep here. In a basketball game, are you going to have to hunt this guy down, which could be an intentional foul, or does it really matter who you foul? You know what I'm saying? I don't know, maybe it makes no sense. All right, how about all the expected values? Are they all more than 1? So what's the fraction that you use? 10 out of 10, right? We've got 10 different boxes in this problem. Okay, it's not a 1 by. Or at least 80% of the boxes expected values greater than 5. You bet. In fact, 10 out of 10 again, right? So we have no issues here. All right, our chi-squared formula is going to be exactly the same, so there's no change here. Observed minus expected squared over expected. But we do have some issues with degrees of freedom. We got a 2 by table here. So here's the formula that we're going to use for degrees of freedom. It's the number of rows minus 1 times the number of columns minus 1. So we've shown our work for expected value. Let's show our work for degrees of freedom. So in this case, it would be 5 minus 1 times 2 minus 1, which is 4 times 1, which is 4. So when we go to our tables, we're going to be looking at 4 degrees of freedom. Let's try square. Yeah.
Why would the second one be 2 minus 1?
Okay, so how many columns do we have? We have 5. And then how many rows do we have in our boxes, right? That's why I didn't want you to draw a line in that homework one, because that would show like 2 different boxes. All right, you guys show me the work for chi-squared. So you got to show me 3 of them. So we'll do the first box. It'll be 72 minus 68.4 squared over 68.4 plus 62 minus 58.6 squared over 58.6 plus, thank goodness for the dot, dot, dot. And we'll go to the very last one. 30 minus 24.6 squared over 24.6. All right, let's get those in our columns. Get them in L1 and L2. Get the observed, get the expected. Use your chi-squared formula. Get all your chi-squareds, all those individual chi-squareds in L3. And let's add the guy up. Put all of the observed in L1. Put all the expected in L2. Calculate each individual chi-squared, and then we want to add them up. Got a number for me? Good.
No, sorry.
You got a number?
13.5.
No. Got a chi-squared issue somewhere. You got a different number for me? I hope these expecteds you gave me were right. Are these expecteds right that you gave me?
Yeah.
May get different expected values? 8.6. 8.5 something or 8.57? 8.57 is correct. You got the same? Armando, you got the same expected values? Check it. Check it. Do you see how you did it? Well, I mean, I'll show you on the example that we have back there what this should look like. Okay, based on the homework assignment, all of your observed should be in L1. 72, 62, 50, 121, 42. Those should all be in L1. And then all these expected values should be in L2. So 68.4, 56.6, and so on. Okay. Then how you do the last column, you do the chi-squared formula. So it's parentheses, the observed, those are in L1, minus the expected, those are in L2, parentheses, squared, and then divided by L2. Still? Really? One of these you entered have to be off a little bit. Do we have confirmation on this? We got some more people out there with 8.5?
I got an 8.7.
That's better. More people got this? You should. Okay. All right, now last step. Let's draw our picture. Right skewed, chi-squared. Here's 0. Here is our 8.57. Let's find the p-value at 4 degrees of freedom. So you go to your charts. Between 5 and 10?
Yeah.
Okay, deep breath. What does this mean? Okay. Hey, assuming that all of these free throw shooters have the same lifetime percentage, there's between a 5 and 10% chance of getting a distribution like this. Unlikely, certainly not impossible, right? Between 5 and 10%. Going to kind of come down to how we set the alpha level, right? In this case, if I set it at 10%, I would consider that p-value enough evidence to say at least one of these proportions are different than the others. And then at that point, I could take a look at this one against this one a little bit more closely and see if it's significant enough. But at least I know now, no, there's someone to go foul. Okay, somebody's different. Okay, so conclusion. Assuming that all the lifetime free throw percentages are the same, there's between a 5 and 10% chance of getting a distribution of free throws like the one we got. Since our p-value is lower than our alpha level, between 5 and 10% is lower than 10% will reject. Therefore, we do have statistically significant evidence to say at least one of the free throw shooters is different than the others. Okay? All right, one last thing now. You should have all of those chi-squareds in L3. So if I asked you the question, which particular box contributed the most to the 8.57, you should be able to look in there and say, oh, it was, and I don't know which one it is.
The 40 and...
This one? Okay. So the third player's free throw misses contributed the most to that chi-squared value. Questions, comments?